Welcome to the fifth lecture on parallel programming with OpenMP and MPI. Today we're going to cover more basics of OpenMP, and at the end you'll be able to use some kind of basic OpenMP toolbox with which you can solve many standard problems that can be tackled with OpenMP. First of all, let's look at so-called reductions. There's a recurring problem in parallel programming for shared memory which we aren't really able to tackle up to now with the features of OpenMP we covered so far. And this is operations across thread local instances of a variable. In this example, we have two arrays A and B and a scalar variable S, which is initialized to 0 before the parallel region. It's first privatized in the parallel region, so private instances of this variable are generated. And then we have a workshared loop, OMP4, in which this scalar product computation is distributed among the threads. So of course, each thread will use its own local private S variable to accumulate its local sum. But then at the end, we have no means of determining what should happen to these local sums and who should sum them up to get the global result. The solution that OpenMP provides here is the reduction clause. It's such a common pattern that OpenMP has very powerful operations that can help you with this kind of operation. So here's what it looks like. This is basically the same code with the exception of this little addition here, the reduction clause. We can use it either on a parallel region or on a workshared loop. Reduction plus :s has the following meaning. Upon entry on the construct, so in this case the parallel workshared loop, each variable in this reduction list gets privatized. It gets assigned a starting value, which depends on the operator that's also specified here. And then each thread uses this local initialized copy to do local work. At the end, the local copies are added up in this case, or put together using the specified operator, and at the end we have a global result. This is all done automatically by the OpenMP runtime. So at the synchronization point, which is in this case at the end of the for loop, the reduction operation is performed automatically. I don't have to do this myself. The result is transferred to the master copy. Essentially, it's also the case that the master copy is added to the result that has been computed within the loop. And there's some restrictions which are basically the same as in first private. So here's the chain of events as we've depicted it also when we study the private clause. We have a shared copy of S, a shared instance of this variable S, which has of course some value. Upon fork, so entry of the parallel region, in this case the parallel loop, we have private instances which all get initialized to 0. At the end of the construct, they're all added up. The inaccessible but persistent global version of the shared variable is also added to it, and this final result is then copied to the shared instance, and this is our final result. This is extremely convenient. There's one condition for this to work, and it will not work. The compiler will complain if the reduction variable is not shared in the enclosing context. So if the variable S in our case had been privatized already on entry to the parallel region, this would be forbidden and the compiler would complain. Basically, all the basic operations that the language, in this case C and C++, provides can be used in reduction operations. So in this list, we see every operation that is allowed in the reduction clause and the initial value that's assigned to the automatically privatized variable. So for example, in the example of the previous slide, we had plus the summation as the operation, and the initial value is 0. For multiplication, of course, the initial value should be 1. The logical bitwise operators and logical operators on actual logical values, and there's mix, max, and min. OpenMP also lets you define your own reduction operators, but that's something for the advanced OpenMP part. So there's some convenience functions, some syntactic sugar that makes it easier to write code. For example, you can specify multiple reductions in one clause. Here in this case, we have three variables, x, y, and z. They should all be summed up after the construct. So I can just summarize this by using one operator plus colon and then a comma separated list of variables. I can also concatenate multiple reduction clauses on the same line if they have different operators, like in this case. Remember that consistency is required. The compiler and also the runtime do not check if you do the right thing to the variable. So for example, if you specified the plus operator on the reduction clause, and then later within the construct you actually multiply into the variable, then you will get wrong results. So do not lie to OpenMP. You will not get correct results. Consistency is required. Here's a slightly more complicated example, and it's a triangular dense matrix vector multiplication. We have three vectors, a, x, and y. A is actually a matrix of size times size, and x and y are vectors. We have a global summation variable s at the beginning, and we open the parallel region. That's actually a recurring pattern also in OpenMP. You should try to open a parallel region as far out as possible, and then keep the threads running while you're doing the work, so that there's as little as possible threads going to sleep and waking up again. We'll come later to that problem, how to avoid this most effectively. So here's our first loop in the parallel region. It's a workshared loop, OMP4, with an unspecified schedule. Which schedule to choose here, that's part of your homework. So this is a dense triangular matrix vector multiplication. I try to depict this operation here. We multiply the upper triangular part of the matrix A with the right-hand side vector, here designated in purple as x, and the result is the left-hand side vector y here in blue. The inner loop goes from m, which is the outer loop index, to size -1, and the outer loop goes from 0 to size -1. So this is how we encode this upper triangular matrix in this matrix vector multiplication operation. And of course, let's say this were a static schedule, so every thread would get the same chunk, roughly the same chunk of the M loop, then we would face a severe load imbalance. So the question is which loop schedule should be chosen here, and you can try this out in the exercises. That's not the point here. Okay, after this loop, we have y of m as a result of this matrix times vector operation. And then we use in a second loop y of m together with x of m, we take the scalar product into this variable s. And of course, this is a typical case for a reduction clause. So we write OMP4 reduction plus colon s. So here's a scalar product. And so in this case, we have two parallel loops within the same parallel region. So which means the team of threads is opened here at the beginning of the parallel region, and it doesn't go to sleep until the final closing curly brace, which is when we have the join and the threads go to sleep or get destroyed. One more thing, you might wonder why there's no privatization clause of any kind here in this first loop. Now, the loop variables, the variable of the parallel loop, m in this case, of course, is automatically private. So we didn't even have to use the int here. We could have left it shared if it had been declared in front of the loop or in the global scope. Also, in the inner loop, we have an in-place declaration int n. So no need here to privatize anything. And the thing that's actually modified in the loop, the y of m, and this is y of m, so it depends on the outer loop index m, and this is the loop index over which the loop is parallelized. So every thread gets a different chunk of m, no matter what the schedule is. The parts of y of m that all threads get are disjoint. So there's no danger of threads writing into their respective memories. So no problem here, no need to privatize anything. All reductions we've looked at so far were reductions into scalar variables, so single values. OpenMP also allows reductions into arrays, which is very convenient if you have to privatize full arrays in order to get the correct result. So here is another dense matrix vector multiplication. If you look into the details, it's a little bit different than on the one on the previous slide because the loop levels are interchanged. So here the inner loop goes over the rows R, and the full left-hand side vector y of r is updated with each full traversal of the inner loop. The outer loop goes over the columns. It does, of course, the same thing, produces the same result in a slightly different order. The problem is with the OpenMP parallelization, because if we now parallelize the outer loop, then this means that every thread, no matter how small the chunk is that it's assigned from the outer loop, each thread updates the full left-hand side vector. And if we don't do anything about that, we will get wrong results because multiple threads update the same variable concurrently. Now, OpenMP allows us to use a reduction clause on the full left-hand side vector. In C and C++, we need a so-called array slice syntax for that. So we have to specify, as usual, the operator, colon, and then the vector. And within the brackets, we need to tell the starting index and the length within this, which in this case is the number of rows. So this will work flawlessly with C and C++. In this case, each thread will get its own local zero initialized copy of the full left-hand side vector y, and they're accumulated, and in the end, they're added up. Of course, this can cause a lot of data to be stored on the local stacks of the threads. So there's a caveat here. You have to be sure to have enough stack space available in such cases. In Fortran, it's actually a little bit simpler. You may be aware that in Fortran, an array is more than just a string of bytes in memory. There's a lot of bookkeeping information stored alongside the array. So in this case, the runtime can actually infer from the array address the length and other properties of the array. So in this case, in Fortran, it's actually sufficient to specify the name of the array, and everything will be automatic. Our next topic is OpenMP synchronization. So OpenMP is a parallel programming model, and of course there are instances where we have to take care that concurrent updates to the same data do not happen in an uncontrolled way. And this is the topic of synchronization. So here's our a very simplified OpenMP memory model. Again, we have shared memory, the threads share the shared memory, and all of them have their private memories, which are, of course, their local stacks. So in this example, we model a variable update in the shared memory, like a read, modify, write cycle. The two lower threads here both want to update this variable A. They want to add something. And if they don't do this in a specified order, if this is not something that's controlled by some mechanism, then the following could happen. Each thread could issue a read. Of course, in order to do something to a variable, to a value, it has to be read into the CPU and put into a register. Then they modify the value within the CPU and write it back. So that's what we call a read, modify, write cycle. Now, of course, there's no way to tell when exactly this read happens and when exactly the write happens on the other thread. So this is something the hardware doesn't control by itself. Which means, depending on the exact timing of this chain of events, different results could occur for the variable A. And that's something we don't want. So whenever multiple threads access a shared variable, and at least one of those threads writes to this shared variable, we speak of a race condition, because the outcome of the whole operation depends on the exact order of events. Synchronization is a means to manage conflicting or uncontrolled accesses to shared data. Now, OpenMP provides a whole bag of options for synchronization, and here in this basic part of the course, we only cover a few of them. The simplest one is the barrier. Pragma OMP barrier synchronizes all threads. So each thread encountering the barrier blocks, so it waits at the barrier until all threads have reached the barrier. Now here's what you can envision what this looks like. So here's the barrier. Everybody has to wait until everybody else has arrived, and then all threads can go on. The barrier has some important side effects, which will become interesting and important later. So one side effect is that all accessible shared variables are flushed to the memory hierarchy. So for example, if a thread has a variable value stored in a register, then the barrier makes sure that this register value is stored into the memory hierarchy so that in principle all other threads can read it using the normal cache coherency mechanism. So if you think about it, that's similar to the volatile attribute in C and C++. Keep in mind that a barrier is a synchronizing construct. It may not appear within work sharing constructs. So imagine a parallel loop where by accident not every thread gets the same number of iterations. If that happens, then different threads encounter the barrier a different number of times. And of course, this would lead to a deadlock. Deadlock is a situation where the parallel program cannot go on because somebody waits for something indefinitely. So barriers may not appear within work sharing constructs, especially not within parallel loops. Now, a barrier can be done explicitly, like with this OMP barrier directive, but there are also implicit barriers in OpenMP, namely at the beginning and at the end of every single parallel region, and at the end of work sharing constructs, unless a no-wait clause is present. And we will investigate this implicit barrier business a little bit further in the following. Now, remember, a barrier is something that's usually implemented in software. Very few modern multi-core processors have hardware facilities for synchronizing threads. This may sound surprising, but that's how it is. So OpenMP barriers are implemented as software constructs. And this means if the number of threads is significant, then the cost for the barrier in terms of time of cycles could also be significant. So barrier sync costs time. Of course, it's important to know how much time it costs, typically a couple of thousands of cycles, depending on the number of cores that you synchronize, and depending also on the quality of the implementation. And then if you know how long your work takes that you do before you encounter the barrier, you could already estimate whether the barrier is a problem or not. If the barrier is a problem, then OpenMP gives you a way to circumvent it in certain situations where it's allowed. And this way is the no-wait clause. The no-wait clause removes the implicit barrier at the end of a work-sharing construct. So in this case, you just save the cost that's implied with the barrier. And there's also another improvement possible if there's a load imbalance within the construct. Then if you remove the barrier, you might be able to hide the load imbalance, because if you don't synchronize, then nobody has to wait for anybody. So if you're lucky, the load imbalance may go away or be mitigated by that. Now, of course, the no-wait clause is potentially dangerous. You have to make sure that race conditions do not occur. So, of course, there's a reason why at the end of every work sharing construct in OpenMP, there's an automatic barrier. This is there for a reason. It's a safety measure. Okay, you can be sure that everybody has finished their work. Every thread has finished what is to be done until they can go on with whatever comes next. So if you remove the synchronization, you have to be really sure that this is allowed by the semantics and the correctness. So here's an example. We open a parallel region, and then there's a parallel loop with a no-wait clause attached. So the parallel loop goes from 0 to n-1. We write to the array a of I, calling some function, some stuff. And let's say there's some other parallel work after this parallel loop that does not require a of I. There could be multiple parallel loops, for example, not referencing I. But somewhere at the end, you will need a of I in the parallel region. So there you could put then an explicit barrier. It's like a deferred barrier that synchronizes all threads and makes really sure that a of I has been updated in its entirety. And then only after this explicit deferred barrier, you can actually use a of I. The program will be syntactically correct also without this deferred barrier, but it may give you wrong results. The problem with this kind of condition, this kind of race condition, is that it may not occur for a long time. It may occur with a very, very low probability, but it's still a race condition. It may happen from time to time. How do we know that the barrier is a problem? How do we see it? What's the phenomenology? Now, in order to study this, let's look at a somewhat contrived example. Here's our beloved dense matrix vector multiplication again, in the form where we update the full left-hand side vector on every traversal of the inner loop. So we know already how we can parallelize this and solve the situation. If the outer loop is parallel, we could add a reduction clause for the left-hand side vector, but here we'd like to tackle it in a different way. So first of all, let's look at how often implicit barriers occur in this case. And of course, we're only looking at a single OpenMP parallel region here, which is actually a combined construct with a work sharing loop. So there's only one implicit barrier. This is okay. Okay, it's the minimum amount of barriers that's possible for this kind of construct. However, we have this race condition on the left-hand side, which we now want to solve in a little bit of a different way. So this program is wrong. Okay, let's make it right. One way to make it right is to parallelize not the outer loop, but the inner loop. The outer loop is subject to the parallel construct, so it's traversed by every thread completely from 0 to n-1. The inner loop is actually work shared. Now, since the loop index is r and the left-hand side vector also depends on r, there's no privatization necessary here, so everything is fine. The race condition is gone. Okay, we still only have one parallel region. However, we have n implicit barriers for the n parallel OpenMP loops encountered here. Now, how do we solve this? Now, we know that these barriers cost time. We'd like to eliminate it. So why not just write no wait, a no wait clause to the OpenMP for loop? Now we still have one parallel region. So there's nothing that can be done against the implicit barriers there. But we don't have any implicit barriers on the workshared loop now because we have specified the no wait clause. If we do this, we have to make sure that on every entry to the parallel loop, every thread that's running gets the same assignment of loop iterations. If that weren't the case, then different threads could work to write to the same section of the left-hand side vector, and you would still get race conditions. So we have to make sure that the sections of the left-hand side array to which each thread writes to are disjoint. How do we do that? We have to tell the runtime that the assignment of threads to iterations is always to be the same. This can only be achieved by static scheduling. So this is a case where we actually need the schedule clause. The default scheduling for OpenMP workshared loops is not defined by the standard, so the runtime could do whatever it wants. In order to be sure that it's static, we have to specify it explicitly as done here. And static is the only schedule that ensures always the same assignment of iterations to threads. So that's why we need it. The result, of course, is now correct. We don't have any cost for the barriers for the workshared loops here. Of course, there's still some residual cost because still the work has to be divided. So there's some cycles spent for calculating the iteration space for every thread. But depending on the size of the inner loop, this could be minor. Now let's look at some performance numbers. So here's performance in megaflops per second for this program versus the number of cores used with OpenMP for two cases. The red line is with using the no wait clause as shown in the previous slide, and the black line is without using no wait, so with the implicit barrier at the end of each workshared loop. The problem size was chosen to be 10,000 by 10,000, so both loops have a size of 10,000. Now here you see that the barrier overhead substantially decreases the performance. So this is the impact of the barrier. The impact is small at small thread counts because the duration of a barrier goes up with increasing thread count, and we see it become hazardous at 4 to 6 threads. Now at the end, we have a performance difference of about 30%. Now this is really significant, and we can avoid it by using the no wait clause. Now, of course, another way to circumvent the cost of the barrier, or to mitigate it, or to ameliorate it at least partially, is to do more work per barrier. If we increase the length of the inner loop to 40,000 compared to 10,000 in the upper example, then we see the gap starts to close because there's more work between successive barriers. So that's also one way to look at the problem. The more work you do between barriers, the less impact the barrier has. So if you know you need the no wait clause to mitigate the barrier impact, be sure to use it with due care. So there's a correctness issue here, and you have to be sure that you don't produce race conditions with that. Now, looking again at these numbers, there are two questions that you could ask here. First of all, is the performance for the no wait, for the barrierless case, as expected? You see the performance tops out here at about 14 gigaflops. Now, if you know the details of this machine, you can actually calculate what the expected performance is. I told you in the roofline lecture. Now, if you don't know the specifics of the machine, you could still learn something. You could look at the number and infer the actual memory bandwidth that's being drawn by this code on this machine. And you can calculate that from the data you know. And then by comparing the red and the black data set, so the performance difference at saturation, you could even infer the cost of the barrier on this machine with this particular compiler. This is, again, homework. A frequent problem in OpenMP is with large parallel or ongoing regions that comprise several parallel loops, but in between the loops you have code that should only be executed by a single thread. And this is what the single directive is for. The single directive has several clauses, and it works on a structured block like the parallel directive. The structured block is executed by exactly one thread. Which thread is unspecified. So usually we use this construct to be sure that the first thread that arrives at the structured block will execute it, while all the others skip over it. Now, at the end of the single region, we have an implicit barrier. Everybody synchronizes. Actually, the single directive is not really a synchronization facility in OpenMP. It's actually a work sharing directive. The work is shared among a single thread. It might sound silly, but from the semantics and how it works together with other directives and clauses, it's actually a work sharing facility. So as I said, the remaining threads skip the block and continue execution. Remember that it's not determined which thread will execute the structured block. Now, since this is a work sharing directive, and more importantly, it contains a barrier, you must not use it within another work sharing construct. This will carry the danger of deadlocks. Remember that the compiler will only help you so much with that. For example, if you use a single directive in a subroutine in a function and the parallel region has been opened somewhere up in the call stack, the compiler has no way of seeing that you're actually doing this. So it's your responsibility to avoid deadlocks by avoiding the nesting of barriers into work sharing regions. You can, if you want, suppress the barrier if you don't need it by specifying a no wait clause. Master is related to single, but it's actually a synchronization directive and not a work sharing directive, because master enforces the master thread or thread number 0 to execute the structured block while everybody skips over it. The major difference to the single directive is that there's no implied barrier at the end of master. So there's no implicit synchronization. So you use it whenever you want one thread to execute something. This thread, incidentally, is thread number 0, and you don't want any implicit barrier. Basically, if you think about it, the master construct is the same as saying if OMP get thread num equals 0, so if this thread is number 0, you execute the structured block. And to make it compliant with non-OpenMP in execution, you could mask out the if with an ifdef on the underscore OpenMP symbol. So this is actually the same, which means the OMP master directive is just convenience to ease writing programs. It's not something that actually adds important functionality. The critical region is a central part of OpenMP synchronization facilities. If you open a critical region, it works on the following structured block, and it specifies that only one thread at a time can execute the block. So this is very different from single and master directives in that every thread that encounters the directive will eventually execute it, but there's no requirement that everybody does so. So there's no synchronization whatsoever. It's nothing that works on a bunch of threads, on a group of threads. So every thread can encounter this critical region by itself. So here I've tried to depict what happens. We have this structured block, which is denoted in gray in this figure, in this timeline figure. And of course, every thread wants to execute the block in our example, but they cannot enter the block concurrently. So whenever one thread gets hold of the block, executes the block, nobody else can. In this case, this thread is the first to encounter the block. And of course, since nobody else has occupied the block yet, it can execute it right away without any disturbance. Whenever a thread is executing the block and another thread wants to execute it also, it has to wait. And depending on the exact chain of events, different threads may have to wait for a different amount of time. So the overarching pattern here is that the block will never be executed concurrently by more than one thread. Remember that the order of execution is undefined. There are some facilities in OpenMP that let you specify the order, but not the critical region by itself. Remember also that if you have multiple critical regions in your program, they all work like a single big lock. So all critical regions in this plain form without any name behind them are mutually exclusive, which means if you have a critical region in a subroutine and one in a different subroutine, and there's even the slightest chance that both will be encountered by the same thread, there will be the deadlock of the danger of deadlocks. This is why OpenMP also provides named critical regions. So critical regions, named critical regions, serve the case of independent, the need for independent critical regions. So in this example, we have a main program with a parallel loop, privatized x variable. Loop goes from 0 to n minus 1. We calculate some temporary value x, and we sum up a function which gets x as an argument, and the function returns a value. We sum up these values into a summation variable. Of course, since sum is shared, we'd like to avoid a race condition. So this update has to be protected by a critical region. Now, within the func function, which is shown up here, we also have something that has to be protected. There's another function called random func, and we can imagine that within this random function, some random number generator is implemented that has some kind of state, like a static variable, that has to be protected from concurrent updates. So that's why we also enclose it into a critical region. Now, if we didn't have this naming scheme, if we just wrote pragma OMP critical in front of both statements, we would immediately have deadlocks because any thread that enters the first region will also enter the second region and then block itself. That's why we separate the two by giving them names. And a thread that enters the psum critical region can enter the prend region without any problems. Of course, again, this problem can be solved in different ways, but here just for demonstration, we've had this contrived example. So regions with different names are mutually independent, and you can choose any name you like. Anything that goes as an identifier in the base language is allowed as a label. The unnamed critical regions have an invisible name that is the same for all of them. So that's how you can imagine the unnamed criticals. The critical region is something that's very convenient to protect concurrent updates, but it's also quite unflexible. Apart from the naming feature, it's also quite costly sometimes, so we'll see examples for that later. The atomic clause is a little bit more specific in that it may allow, depending on the hardware and the software implementation, very efficient, very fast updates which are protected from other threads. So here's the general form, pragma OMP atomic. There are some clauses, and there are also other forms of this construct. Here we use the simplest form, where the atomic just works on the immediately following expression statements. So what it does is it ensures that a storage location, which is part of this expression statement, is accessed atomically, which means the full access cannot be interrupted. Whatever you do to this storage location that's modified in here, the whole process, read, modify, write, cannot be interrupted. So that's a very efficient way to protect an update to a variable. Remember that that's not a structured block. It's really just one statement. So the clause, the atomic directive only applies to the statement immediately following it. This expression statement has a very specific form. Here's the 7 possibilities you have: x plus plus, x minus minus, and then the prefix forms, and then x whatever equals expression into others. So these are the forms that the expression statement can take, and the compiler will infer from this statement under the hood what has to be done. There are, as I said, some variants of the atomic directive for other cases, like when you only read a variable, or you only write it, or you capture a variable into some other variable. So again, why atomic? Why do we need this? Why can't I just use a critical region for that? Now, first of all, some processors have hardware facilities for atomic operations, reading, writing, updating. So atomic may be more efficient because of hardware support. There's no guarantee for that, of course. Under the hood, atomic could still be implemented as a critical region with the same facilities. Secondly, and probably more importantly, atomic allows for protecting updates into individual data elements, which critical regions cannot do. It's just more flexible. Here's an example. We have a parallel workshared loop over I. We calculate the temporary variable t by calling a function, and this function gets as an argument a table entry of index I. Depending on the outcome of this function, whether it's smaller than 0 or not, we update a certain element of array X. And now here's where atomic comes in. Since we don't know the actual outcome of this table lookup, we don't know which of the x's will be incremented when t is smaller than 0. The atomic gives us a way to update the whole range of possible x values, the contents of the x array, individually per element. So this is very nice. It updates, it allows us to update different x entries which do not block each other. So the runtime will recognize that if one thread encounters an atomic and it updates a different x than another thread that also encounters the atomic, then those two will not block each other. This cannot be done in this efficient way with a critical region. If you just wrote pragma OMP critical in front of this update, then all updates to any part of X would block each other, and the whole thing would be much less concurrent than it is in this form. Again, remember, there's no guarantee that atomic is more efficient than critical. So in practice, you may not see a difference, but if the compiler and the hardware supports it, it may make a huge difference. This almost concludes our beginner's OpenMP toolbox. There's one topic we haven't touched upon yet, and this is OpenMP Affinity. Now, what's Affinity? There's one thing you should take home from this part of the lecture, is that OpenMP Affinity matters. It's really important. Please keep that in mind. Remember when we gave you an introduction into the hardware structure of modern multi-core nodes and all the bottlenecks that this architecture is plagued with. So all those bottlenecks and the rich topology that is used to put them together means that it does matter where threads are running. It does not make sense to just leave it to the runtime, to the operating system, to determine where the threads should be running within the machine. So here in this example, we see 4 threads running on the first hyperthread, respectively, of the 4 first physical cores of the left socket. So that's like an orderly fashion. Now, we could also leave it to some runtime decision or to the kernel to decide where to run these threads, and it may turn out like this. So two threads may end up on the same physical core, running on the two hyperthreads of this core, while the third thread may be running on a physical core, being able to move between the hyperthreads, and the fourth thread may even be running on the other socket. These two situations are not the same for most programs. So it doesn't matter where the threads are running. And even worse, it's up to you. There's no automatic mechanism, no magic that will read your mind or determine what your program needs. So the system will not magically guess what's best for you and the performance of your program. To prove this, here's some data. I ran a stream benchmark. Stream is a very popular benchmark, and one part of it is this OpenMP parallel array computation. Array A equals array B plus scalar times array C. And for this experiment, I used 48 core node. It has two sockets with 24 cores each. Each socket has 4 CC NUMA domains with 6 cores each. So this is an AMD Naples system. In the first experiment, we didn't use any pinning at all. So the threads were left to their own devices, and whatever automatic mechanisms are there, they were used or not, I didn't care. And I ran this benchmark for every number of threads from 0 to 48. And for each number of threads, I ran it 30 times, and I reported the median of all measurements. That's the little black dot, and the whiskers denote the min and max bandwidth measurement. And you see there's a huge variation in performance readings. So even if the number of threads is constant, the spread in outcomes, in performance outcomes, is huge if you don't do anything about affinity. Now, to show that it's actually the affinity that generates this huge variation in runtime and in performance, um, we conduct the same experiment with so-called compact pinning. And this means that for any number of threads, the machine is filled from left to right, so consecutively filling the physical cores of the machine with threads. And there you see each of these dots is actually a mean and two whiskers for the min and the max, and the whiskers are practically on top of each other, which means there's practically no variation in the performance from measurement to measurement, from run to run. Now, the particular form of this curve can be explained. So here up to 6 cores, we have the typical saturation pattern with the particular property of this processor that a single core can really almost saturate the memory bandwidth. That's a nice feature of the modern AMD processors. And as we leave the NUMA domain and go beyond to multiple NUMA domains, we have this linear rise in performance, which can be explained. I might do that later in the lecture. So the point here is that the run-to-run variation is almost gone. There are, however, more reasons for caring about affinity apart from the elimination of performance variation. One other important reason is making use of architectural features. In these complicated topologies, we have shared and common or local resources, and you might imagine algorithms which actually make use of a shared cache. So an algorithm which only makes sense or only works in the most efficient way if multiple threads actually can share a cache. Now, if you don't know which thread is running where, there's no way of knowing which threads can share a cache. So affinity and pinning is a prerequisite for that. Also, you may want to avoid resource contention if you know that the memory bandwidth of a single CC NUMA domain is already saturated with 2 or 3 threads, then it actually doesn't make sense to run more threads than that. Also, to determine how many threads will be running on one NUMA domain, you need affinity features. So there's lots of reasons for caring about affinity. There are many ways to pin threads to resources with OpenMP. But there's only one way that's actually backed by the standard. It's debatable whether or not this is really the best way to do it. But since it's part of the standard and may be improved in the future, I think it's worth a try. And at least on the systems we're going to encounter in the exercises, it works flawlessly. So thread affinity, as implemented in the OpenMP standard, has as its central concepts a processor and a place. Unfortunately, the naming scheme chosen here by the standard is a little bit unfortunate. A processor in OpenMP nomenclature is the smallest hardware entity which is able to run a thread or a task. Now, in terms of hardware structure, this is an SMT thread or a hyperthread. So in OpenMP speak, an SMT thread, a hyperthread, is a processor. A place comprises one or more processors, and whatever you do with thread pinning, this is done place by place. So a thread is always running on a place, and a place could be one processor or more processors. Now, if a thread is running in a place, then and if this place comprises more than one processor, then this thread can move freely between the processors of one place. So these are the three things you need to remember to understand the thread affinity concepts in OpenMP. Now, what are the options for specifying places? The standard specifies 4 options for places: threads, cores, sockets, and whatever the name is, threads, cores, or sockets, and then in parents behind it an integer number. Now, these designators, threads, cores, sockets, are called abstract names, and the standard only defines these 3 abstract names. A particular OpenMP implementations or a particular compiler may define more than that, but those 3 are the only ones that are in the standard. Now, generally, you can say that if OMP places is set to threads, then one place is one hardware thread or hyperthread or SMT thread. If OMP places is set to cores, then one place is all hardware threads of a single core. In modern Intel and AMD processors, that's usually one physical core comprising 2 hyperthreads. But there are examples of CPUs in which one physical core has up to 8 hyperthreads. If OMP places is set to sockets, then one place comprises all hardware threads within a socket, which could be a considerable number. And then, if for some reason you want to restrict the placement strategy to a certain subset of places, you can follow one of these abstract names with a number in parents, and by that you restrict the number of places available. So for example, if your machine has 20 cores, but you only want to address for some reason the first 10 of them, then you could put a 10 as an argument here, and then the whole placement will only be done on the first 10 cores of your machine. So these are the options you have for assigning to the OMP places environment variable. The affinity mechanism in OpenMP works with environment variables. You can also influence it from the running program by using clauses, but the general way is by setting environment variables. Now, you may use these abstract names, and they are really convenient because they are mapped to actual hardware entities. If you read the standard thoroughly, you will see that the actual behavior is implementation defined. So there's nothing in the standard that says a thread must be a hardware thread, but it's actually the sensible choice, and all compilers we know do it in this way. Now, if you need full control, you could use explicit numbering for specifying the places. So in this example, we have 8 places, each consisting of 4 processors or hyperthreads. And if we use it like that, OMP places equals, and then there are groups of 4 designated by these curly braces, and these numbering is consecutive, then we have 8 places. Each place has 4 hyperthreads. There are shorthand notations for that. So in this case, 0 colon 4 means starting at index 0, I want 4 processors. And there's even a shorter way of handling it. I could designate a group of 4 repeated 8 times with a stride of 4. And that would be a shorthand for this lengthy designation. here in the first bullet. However, again, the actual behavior is implementation defined. And also how these places are numbered is a function of the OpenMP runtime's understanding of the hardware. So you need to be sure that the OpenMP runtime of the compiler understands the structure of the hardware. Whatever you do, always check that your threads are running where they should be running. Now, specifying what a place is only half of the way to correct pinning. The second thing you need to say is how the places should be populated. And this is what the OMP procbind variable is for. You could also use a procbind clause on a parallel region to influence this at runtime from within the program. Now, here are the 5 options for OMP procbind. Only 2 of them are relevant for most cases you will encounter. Those are close and spread. If you set OMP procbind to close, then you specify that threads should bind to consecutive places. So whenever a new thread is generated in a team, it will bind to the next available place. Whereas if you say OMP procbind equals spread, then this specifies that threads will be spread out, they will be scattered evenly across all the available places. So if you want your threads in your OpenMP thread team to be scattered among the whole machine as far apart as possible, then you would use spread. That's actually a quite common scenario, and in many cases, this is what gives you the best performance, because spreading out the threads will mean each thread will get the most cache per thread, because we usually have shared caches in these machines, and it will also get most memory bandwidth per thread, always assuming that you're not using all the places available in the machine. If there are more threads than places, consecutive threads are put into individual places, and this is in some other pinning mechanisms called a balanced placement. So let's say we have 10 places, but 20 threads, then thread number 0 and 1 will be put together on the first place. Thread number 2 and 3 will be put on the second place, and so on. So this is called balanced placement. So here's how you could use it in practice. You set the number of threads, 4 in this case. You set OMP procbind to close, specifying that each new thread will be assigned the next place in the machine consecutively. And OMP places is cores, which says that place comprises all the hyperthreads of a physical core. And then your binary. Now here's some examples from practice. How to pin threads in certain situations. We have Intel Xeon node with SMT enabled, so Intel server processor. Each core has 2 hyperthreads. Each socket has 10 cores. We want to run 1 thread per physical core and fill 1 socket. So this is very similar to the situation we have on the ME cluster where we do the exercises. We want to run 10 threads, so OMP num threads is 10. We want to put every thread on its own separate physical core. So OMP places is set to cores, and OMP procbind is set to closed, because we want to address the first 10 physical cores in the system. Here's a more complicated case. Intel Xeon Phi is a now outdated coprocessor with up to 72 cores. Each core has 4 hyperthreads, 4 SMT threads. I want to use only 32 of these cores. So I leave the rest untouched, and I want to run 2 threads per physical core. So the overall number of threads to run is 64. The number of places should be 32, and 1 place should be 1 core. So I'm designating this, I'm specifying this by saying cores and then as an argument 32. This restricts the whole placement mechanism to the first 32 cores in the system. And OMP procbind should be close. Now, actually, in this particular example, spread will have the same effect because I'm using more threads than their available places. And then the 2 behaviors will be the same if the number of threads is a multiple of the number of places. Again, Intel Xeon server processor, 2 sockets. I want to run 4 threads per socket, but I do not want to bind the threads within the socket to cores. I want the 4 threads per socket to be able to roam freely among the cores. Number of threads is 8. OMP places is sockets, because that's the unit in which the placement should be done, and all threads put into one socket should be able to move freely, and OMP proc bind is close. Again, the number of threads is a multiple of the number of sockets, so it doesn't matter in this case whether I use close or spread for the proc bind setting. And finally, Intel Xeon server processor again, 2 sockets. I want to run 4 threads per socket, but I want to bind the threads to cores. Again, I want to run 8 threads. OMP num threads should be 8. OMP places is cores. Then, in order to spread out the threads evenly across the system, I'm specifying OMP proc bind equals spread. Here it does matter. If I had written OMP proc bind equals close, I would only be using the first 8 physical cores on the first socket of the machine. So whatever you do with this pinning mechanism in OpenMP, always prefer abstract places instead of hardware thread IDs. Do not use hard-coded thread IDs, because this could backfire if for some reason you don't really understand the structure of the machine or the numbering of the resources. And it's always better to rely on these abstract places. If the OpenMP pinning mechanism does not do what you want or cannot express the pinning strategy you want to implement, there are other facilities which I will tell you about in due time. Okay, this wraps up our beginner's OpenMP toolbox. Here's what we covered. I told you about parallel regions, how to open a parallel region and make threads execute a block of code redundantly. We looked at the workshared loop construct, how to assign iterations of a for loop to different threads so that the work is actually shared among the threads. We talked about data scoping, specifically shared and private variables and also first private variables. I showed you how to do basic reduction operations with standard operators on scalar variables and arrays. We dived a little bit deeper into simple synchronization constructs. There's more than what I told you, but this should suffice for the moment. We looked at barriers and no weights and how you could use no weight to your advantage and what it might cost in particular situations. We looked at criticals, named criticals, and atomics. Atomics is a particularly elegant way of protecting certain statements that only update one element in memory. And we looked at single, which is actually a worksharing construct, and master. OpenMP Affinity, as defined in the standard, is really easy to use. It may not cover all the cases you might encounter in practice, but it's a good place to start. Never run an OpenMP program without specifying Affinity. Of course, there's more, and a little bit more of the advanced stuff in OpenMP will be the topic of the next lecture. Thank you.